Bismillahirrahmanirrahim. Welcome to Diode and Application Season 2. Once again, we welcome you in this series. While this series is going to terminate, and of course, this is the second last video of this series, and the last episode of Diode and Application. In the last episode, we will discuss the troubleshooting and it's relevant in the upcoming episode. While in today's lecture, we are going to discuss a new topic, and that is not a very not you can say very important topic, but we want to cover it because it's relevant to diode. So we are going to discuss a current regulator diode. So these are some pictures. You can see that this is a current regulator diode. Often some students may see this but not recognize with it, but now you can see that this is a current regulator diode. Most of the cases, these different types of devices available, different types of the elements like this. For example, this is a current regulator diode, and basically we will discuss this current regulator diode in when we are going to discuss bipolar junction transistor and other types, because this is formed by joining the MOSFET, and this is another categories. So we will discuss in the next series these type of things, and we will cover it in details there. We'll just cover just introduction of this current regulator diode here. So this is the symbol, and anode is represented by a circle here, empty circle, and once again cathode is identified by this straight line, right angle to the cathode. Anyway, this is the another look of this representation. And the current regulator diode, as the name indicates, regulation. Once again, its purpose is regulation, as the Zener diode its purpose is to in the case of the Zener diode's purpose was, as we seen that the Zener diode maintains a constant voltage. So so here the current regulator maintains a constant current, but usually some appliances, for example some circuits, are sensitive and they don't support much higher ratings. That's why we uses the current regulators as a protection sometime, because it maintains a constant regulation, constant voltage. After a certain even exceeds in the volts, it allows to increase in the volts in a huge range, but it still maintains a constant current even the entire range of the voltage. The voltage range is usually wide, so we can use this. Its application is in that case. If you are confusing about the current regulation, mostly the voltage regulation is used and current regulator is rarely used. The current regulator diode is often referred to as a constant current diode. Rather than maintaining a constant voltage, the Zener diode does it maintains a constant current. Operates in forward bias. Its normal operation is in forward bias operation. It is not used for the reverse bias. It's very worst in reverse bias. It's just like a conductor, and if you change the polarity in reverse bias, it's just like a normal conductor, doesn't have any even resistance or a potential barrier or so on. So it's not designed to operate in reverse bias. Forward voltage, it takes approximately 1.5 volt to 6 volt, and after this drops of voltage, or you can see that after this volts, it is tries to maintain a constant current, and it depends upon, of course, manufacturer to manufacturer, and it is mentioned in their datasheet. But this is the range, as in the case of the normal p-n junction diode, the range after which it maintains a regulation is 0.7 volts drop. After that, it does not exceeds in voltage, and then current increased. And here in this case, after the 1.5 volt, or you can see 6 volts, there is not exceed in a current. It will attain a highest peak in this region within 1.5 or 6 volt, and after that it attains a value of a current, and it tries to maintain this value that it gains in this particular region. So The constant forward current is also called the regulator current, and it is designated as IP. This is the constant forward current regulated, and this is the graphically we want to understand. This is the graph of the forward bias, this region from here towards this side. From here, please note that this is the 0, and here it's 20, 40, and increasing in a huge number. For example, this one block is single block, it has a magnitude in lengthwise 20, while here you can see that this is just -1, -2. So this scale is not constant scale. This scale is not chosen constant because in the reverse bias you can see that it's just negative, even it doesn't touches the -2, and it's you can see that current is exceeded in the negative region, and it's doesn't maintain any constant reverse current or anything else. So if we select here -20, so we cannot monitor its the resistance of this curve, and does not even we can see that its behavior, it just looks like an ideal case, and it's like this. So that's why it's this scale, while here in this case it has a wide range of the voltage. That's why we selected a bigger scale. So here you can see that 1.4 volts is just like this point, okay, and this point is approximately, let's say, 6 volts. Okay, this is 6 volts, and this lower point VL is when the current is at this point. We can see that our current is also at the lower point, and it tries to now maintaining, and you can see that the look of the graph is now little bit changing at this point VL at the rate of IL, and that's what I said, that it tries to attain the peak after within the 1.426 volts, and after that it attains any value, then it tries to maintain or regulate the value that it attains within this voltage range. And for example, at 6 volt it attains 3 milliampere current when our knee point at VK, this is the impedance, and usually its impedance is high. Impedance is in case of the current, you can see that the current is not exceeding. It means there is an impedance or a resistance, internal resistance of the device that is tries to decrease or not increasing, tends to maintain a constant current. So it is almost a resistance in a way of current that maintains a constant current. So its impedance is really high, and it's mentioned in data sheets. So it maintains a constant throughout the approximately 3, here in this case 3 milliampere constant current throughout, and this is the peak operating voltage. For example, it's here 100 is the peak operating voltage, and of course this is a worst condition, as we already mentioned. In case of the Zener diodes, we should have to be within the 20% at least. We have to tolerate 20% inside the peak operating voltage and knee points. So that's why we always take some test voltages, test currents within these certain limits. And IP, that this is the regulated current, as in the previous slides mentioned, that when our voltage is at test voltage, and this is, for example, let's say 25 or anything else, any other value, and when our impedance is mentioned in the for example in the data sheets, usually the impedance is in often mega ohms. Also depends upon the type of the resistor, and it's designed for how much amount of peak, how much peak value it's trying to regulate the, for example, current. That, as in the last slide, you can see that it's just 3 milliampere, and it depends upon the current we want to regulate, and the resistance value depends upon the magnitude of the current. So current regulator diode, the diode does not have a sharply defined reverse breakdown, so the reverse current begins to increase for the reverse values of a anode to cathode. For the value less than 0 volt in negative, the device should not be operated in this region. Here you can see that if we goes towards this side, V anode cathode voltage goes to this side, its current is increasing very rapidly. I already explained, even this is you can see that not a constant graph, not a constant magnitude. Here this side, this scale is bigger, this scale here, this side, one box it has a supposed to be 20 points here, but here just a -1 magnitude, -2 means to say even very smaller, we cannot imagine. So that's why we say that this is not designed to operate in the reverse bias region. Regulation starts from the knee point. Here this is the knee point, after which the regulation continues, and the maximum peak point ends at peak operating point. After this point it will go into the breakdown region at any point. So it's better to operate within the limits. So test current is always tested at the best suited value, as in the case of the Zener. When we are talking about the Zener's graph, we see that the test current or test voltage was always you can see that tested in the middle of the graph, as we already take. So the test current at the rate of test voltage, high impedance, as I already explained, it has a high impedance. So this is a question for you: between what two voltages does a current regulator diode operate? I already answered in my discussion, but the question is up to you, and this is a very later question. So this is a time to terminate this session. This is a very today's lecture is very short, very short, and of course we will discuss some troubleshooting of the diodes without wasting of another time. I've tried to terminate my session, and here, watch and glow. See you next time.